third problem. Okay. So we have a triangle with angle C is equal to 90. So I'm not sure the best way to do this. I think I'll just do it like this. Name it as O or something. So, whoops. So C is a point on this circle, and D is the foot of the altitude. So that's D, and X is a point on CD. K is on AX, such that BK equals BC. Okay, so we have this right triangle, and we want BK equal BC. This problem looks really familiar, actually. I think we might have looked at it really quickly, but not gotten to solving it. Actually, I think DAT, you might have said you saw this before, if I remember. So BK equals BC, and AL is equal to AC. And the circumcircle of DKL intersects AB at another point. T. We want to show that ACT equals BCT. Does that mean they're both 45 degrees? I think so. So let me check that out. I don't think it was this exact problem. Maybe it's, yeah, so we want to show ACT and BCT are 45 degrees. It's kind of interesting. I'm going to hide some stuff. Probably can hide that. We'll just have to remember ACL and BCK are isosceles. So we have two isosceles triangles, ACL and BCK. Like that. This is interesting. So yeah, X is a variable point. And then everything gets constructed from there. As well, draw those two. Pascal. Yeah, it looks like maybe we can. Oh, sorry, I missed Urjan's way of showing JH is parallel to AB. Oh well. So yeah, doesn't it? It looks kind of familiar. I don't remember if this is what we were supposed to prove, but it's the same configuration, right?
We can start by constructing two circles.
Two circles?
With center A. This is through C. Yeah.
Yeah. These, all right.
This is used in these problems.
Okay. Yeah, I might need to shrink the diagram. Oh, did you proved it with projective geometry? This exact problem? Does CT pass through this point? I don't think so. Maybe XT does? Oh, the previous one. Interesting. Yeah, it looks like XT passes through that point. I don't know if that's obvious. Are these angle bisector? Maybe this is the incenter. You prove
Yeah,
that
can you name that point?
Yeah. So it looks like it's maybe
In
the
IMO, they asked EK equals to EL.
BK is equal to, EK
EL.
is equal to EL. So maybe E is the center of that circle.
No, it's not.
It's not. It almost looks like it there, but I don't, but yeah, you can, yeah. So in the IMO.
EK is equal to EL.
Okay, yeah, so from the IMO problem, EK is equal to EL. Yeah.
No, I don't think it is from IMO 2010. Could you draw the line that pass through A and B and perpendicular to BX and AX? So X will be the ortho center of that triangle.
Okay. So yeah, hold on a second. So yeah, the configuration is IMO 2010, but it didn't ask for this exact thing. So maybe it's, okay. So yeah, so that point right there. So X is the orthocenter of that triangle.
Yeah, it should be.
F is the orthocenter of AXB. Maybe I could draw the perpendiculars to make it clearer. Sorry, AXB.
You intersect KL with BC.
Yes. Yeah, I'm gonna have to change the diagram because yeah, they're really close to being parallel.
About that point, X, E, T look collinear. So if you take that intersection with KL and AB, then you will form a harmonic bundle.
Okay. Yeah, I saw that X, E, and T look collinear. But yeah, I don't think E is the incenter. I thought it was before, but let's see. So yeah, so it doesn't. Wait, is T the same point? Oh yeah, T is always going to be the same even when I move X around. So really, maybe we only need to show it for one special case of X.
Are X, E, T collinear for sure?
Let's see. Yeah, I'm pretty sure. Let's see.
Then we want to prove that KL, AB, and the X X bisector, angle bisector concur.
Oh, so you mean like draw IC, for example? Let's see. But hold on, let me make this look better. It's too much stuff.
Maybe we don't need to draw IC.
Okay. Because we want to show CT is an angle bisector, right? So I guess that's what made me think of it, right? Well, because that would mean angle ICT is a right angle, right? I think so. Yeah. So I don't know that, but if that were true, it would solve the problem. Because if angle ICT was 90 degrees, that actually means angle ICA is 45 degrees. But the thing is, since X, E, and T are collinear, A, B, T, and I are in harmonic conjugation. And the problem wants us to prove that CT is the angle bisector of A, C, B. But if A, B, T, and I are in harmonic conjugation, and if this were the bisector, then angle ICT would have to be 90 degrees. That's a theorem about harmonic conjugation. Yeah. So basically CA and CT are isogonal in triangle ICB. I don't know if that does anything, but. And these circles are orthogonal. So I don't know if there's something special about like orthogonal circles. Yeah. All right, looks like we have someone new joining. Hi, Khan. Thanks for joining us.
Hey, Michael, I'm a little late.
Oh, it's all right. Don't worry about it. So yeah, we're on our third problem. But yeah, you can feel free to join or leave when you need to, because I know it's at different times in different countries. All right. So yeah, this is our third problem. So I did the USA team selection test today. Can I hide F? Yeah, I can hide F. That might make it easier.
So you just drawn the configuration?
Yeah, so we drew a couple extra things too. So hold on just a second. I'm going to hide a few things. But yeah, DAT, let me know if you want me to draw it back in later. So, oops. So yeah, we have a right triangle where C is the right angle, and then we drop the altitude, and then X is any point on the altitude. And then we draw AX and BX, and then we draw L on BX such that ALC is isosceles and we draw K on AX such that BCK is isosceles, and then we want to show, then we draw the circumcircle DKL, and it intersects AB at point P, and we want to show that basically CT bisects angle ACB. So that's the same as saying angle ACT and BCT are 45 degrees. So that's what we want to show. And everything else after that I just drew in.
Can you intersect BL and AK with circles?
With the circles, okay. Let me see if I've already, yeah, so I can just unhide it. Okay, so with these circles,
Yeah.
Okay. So that's J and M.
Yeah, these are enough.
All right. And then I wonder if J, M, and I are collinear. Ah, looks like it. Or is that tangent? No, I don't think they're tangent to the circle. Because, but it's interesting that they're
I
collinear.
draw the circle JKLM.
Yes. Here we go. All right.
How BL is tangent to the circle.
Yeah, I was gonna say it looked like
Lost one.
AL and BK are tangent to it.
Well, we can prove it by power of point. AC squared equals to AK times AM, and AC equals to AL.
Okay, so AC is equal to AL, and you said AC squared is AK times AM. Because AL squared is
Equals to
AK.
AC squared.
AC squared is AK times AM.
Michael, the circle you draw is the circle with the center F that I have mentioned before.
Okay, so the circle. Oh, this is center F, where F is the orthocenter.
I think we are almost done.
Okay.
Because we will prove that JK and ML intersect on T. Then we will prove that I is on MJ. So we have that IABB is harmonic bundle.
Okay. Say this one more time. Okay. So, yeah. So dat. So did you know before that F, if F is the orthocenter, then it's the center of the circle?
It must be because if F is the orthocenter, so AC square will be equal to AK times AM.
Mm-hmm.
No, could you unhide FAFB and some, yeah, and yeah, and the point G and H.
Okay.
Yeah, that's look better. So we define L as AL is equal to AC. So AC square is AD times AB. That will be AH times AF.
Mm-hmm.
Yes. And yes, so AL square will be equal to AH times AF. So FL will be perpendicular to AL.
Ah,
Yeah.
interesting. Okay. JKMMLL. So T is the intersection point of JK and ML. Okay. All right, let me start writing this up. So where should I start? So Serdar, does your solution use point F?
I guess it doesn't.
Okay.
It can stay.
All right, I'm just going to leave it on the diagram just because I think it's an interesting idea for now. So I think Dat had a different way to show that MJKL is cyclic. Okay, so I'm going to say, hold on a sec. So first, let me name the points. Okay, so let KL intersect AB at I. In fact, I don't think we need point E, right?
It can stay.
It can
We
stay.
need it because intersection of JK and ML, let it be T prime. Then we know that T prime is on X, E, and we know that it's on A, B from Pascal.
Okay. To answer Khan's question, yeah. So we're going to do more problems after this one. So I have 3 more lined up, but we'll see how many we get through. So, okay, I'll start. Let KL intersect AB at I. And then so what points did we I forgot everything we did. So how did we define this M? Okay, let AX intersect. Okay, I'll just say let omega A be the circle with center A through C and L. I think we've solved it. Hold on just a sec. And then define omega B similarly. Oh, not yet. All right. Omega B similarly. And then let, we need to show IJ and M are collinear. Okay. Let AX intersect omega B at M. Omega B at M. And let CX intersect omega A at J. Or let BX. Omega A at J. Okay, and then we want to show JMKL is cyclic. So we could do it. So Serdar, how did you know? Okay, so we use Pascal right now, I think. So
we use it and we see that intersection point is on AB.
Okay, so by Pascal on JKMMLL. But we still don't know that E, we still don't know these three concur at E, right? So is it still okay to use Pascal if we don't know that?
No, we know that the tangents at K and L intersect on E.
Oh. Wait, hold on, sorry. AD is the radical center.
It can be proved that X, E, and T are collinear.
Okay, X, E, and T are collinear. Okay, so
When we define E to be those tangents, if we know that they are tangents.
oh, so let E be the intersection of the tangents, but and then we can show that KE, we could show that KEB are collinear, AEL are collinear, and XE and T are collinear, basically.
Have we showed that those are tangents yet?
I don't remember us showing that these are tangents.
No, we show that from power of point.
Oh,
AL
okay.
squared equals to AC squared equals to AK times AM. But we didn't prove that XET are collinear yet.
Okay, so
All right.
Delete XET segment.
Yeah. Okay, so we have
We can probably like so we know EK and DL are tangents. Then we can probably do like some Broker theorem to show that X, E, and T are collinear. I think I remember
Yeah, that
hearing
looks
that just like
familiar.
a theorem, but
I think it's just Pascal's theorem,
you
right?
can use like polar to prove that XE and T are collinear. If EK and EL are tangents, it's easy.
Yeah, because XT has to be the polar.
So we don't know T yet.
Oh, what?
We don't know the T. Intersection is T.
Wait. Does JK and ML concur on AB and that one is T? Is that how you define it?
So I define J as the intersection of so yeah, we should probably get rid of this circle for now, right? So yeah, I'm trying to think of the right order.
Yeah, can you delete this circle?
Yeah,
I did.
like this.
So let's define T as the intersection of XE with AB. Then we know that T is the intersection point. So we can try to prove that KLDT is cyclic.
So wait, T, we're not, are we defining T as the intersection of K, J, and ML?
We define it as intersection of XE with AB. But from Pascal, we know that JK and ML passes through T.
Okay. So let T be the intersection of XC with AB. And by Pascal's theorem, JK and ML pass through T.
Pascal and the polar thing.
Okay.
From Pascal, intersection is on AB, and from polar thing, the intersection is on XE.
Okay. And polars or power of a point? Both. Good, because wait, hold on a sec. So let me write. So we have AL squared is AC squared is AK times AM. So AM. And so that means AL is tangent to the circumcircle of KLM. So when we repeat a letter while using Pascal, it means it's like a hexagon, but where one side has length 0. So it's like, imagine a hexagon where you take two vertices and you squish them together so close that it's like they're the same point. That's basically what we're doing. So, okay, so AL is tangent to, but wait, how do we know that KLMJ is cyclic? So DAT, I think, showed a way to do it using the orthocenter.
The power of point easily shows this because CD is radical axis and xk times xm equals to xl times xj.
Okay. Okay, so I'm sorry, I'm gonna add that. So CD is the radical axis of both circles, implies and so that implies xk times xm equals xj times xl, and that means that jklm is cyclic. And then we have this, so implies AL is tangent to jklm. Let's see how this works. Okay, so we have JK and ML intersect at T, and then, all right, so I think we've got pretty far. Now we have to show IJ and M are collinear. Was that the last step?
No, we should first prove that KL TD is cyclic.
KL DT is cyclic. Yeah.
Then we can show that J DT, but I don't know how to prove. After that, from radical axis theorem, I is on JM.
Okay. All right.
Okay, so I will prove KL DT is cyclic.
Okay.
Right, that's just the
So-
micro point, right? The micro point.
Oh, the McHale point?
Yeah, of JKLM. So it's the altitude from the center of F onto the like the polar of X.
Okay. So yeah, so by McHale's so D is the
We don't
McHale
know
point.
that I is the intersection of MJ and KL. We need to prove that.
Oh yeah.
I think like AB is the polar of X. So
Is it obvious that AB is the polar of X?
yes, because A lies on the polar of, like JL is the polar of A. So A lies on the polar of X, and similarly B lies on the polar of X. Then AB is the
Okay.
polar of X.
So JL is the polar of A. I like it. And KM is the polar of B. And And that implies that AB is the polar of X. So that means that IJ and M are collinear. And it also means that D is the McKell point of the JKLM. So DKLT is cyclic. Okay. D is the McKell point of JKLM, which implies that DKLT is cyclic. So yeah, I guess really like we should have called this T prime and then said T equals T prime. So I can do that right now. Just to be, I think you guys all know what I mean, but just for the people on YouTube. So we could call this T prime. And this T prime. And then we have DKLT prime is cyclic. So we have T prime equals T. So I'll just add that right here. So T prime equals T. And then so basically by Ricard we have A, B, T, and I. A, B, T, and I are in harmonic conjugation. So CT is the angle bisector, right? So is that right? Wait, how is it true? How do we know that A, B, T prime, and I are in harmonic conjugation? Wait, sorry, that shouldn't go through X. There we go. But how do we know that A, B, T prime, and I are in harmonic conjugation? Oh, because, wait, never mind. Because we don't know, we never,
what?
because I, K, and L are collinear. Yeah. Wait a second.
Because of the complete quadrilateral.
Yeah, so, okay, so I'm trying to remember how to finish this off. So we want to show.
We need to prove that ICT is 90.
Yeah, I was going to say we need to show ICT is 90 degrees. Can
you intersect IX with FT prime?
Yes.
TX with FI.
Ix with ft prime.
Yeah.
Waiting for that thing to go away. Sorry, my screen is freezing up. Okay. So this point right here,
Yeah.
right? So basically you want to show ICNT as cyclic.
Okay, I guess. Can you show the other intersection of the circles? The first two ones.
Oh, okay. Yeah, so like down at the bottom.
Can you name it?
Yeah, let me shrink some stuff. Hold on.
Wait, what are we doing? Like, how can we use these things to prove that the two angles is equal? Like, what is your idea?
Michael, we don't need that point I. So we could calculate TA over TB and CA over CB. Maybe.
Okay, so angle bisector theorem.
Yeah.
No,
So
I found the proof. I was talking about that.
Okay, hold on just a second. I'm going to first finish Serdar's idea, and then I'm going to look at your idea. Okay, so let me draw that point. That's interesting. It shrinks the space between, it doesn't shrink the size of the text, but it shrinks like the space between it. Interesting.
Inversion
Mm-hmm.
with reduce Fn times Ft prime. Square root of Fn times Ft prime.
Okay, hold on. So
C to P.
it takes C to P. Fn times Ft prime. So if you take an inversion with that product, it takes C to P. Okay.
This implies C and T prime P is cyclic.
Oh, so how did you know with, I was assuming that somehow you already knew it was cyclic, and that's how you, how do you know that like, how do you know that inversion does that?
Because I guess we know XCP is harmonic.
FCXP is harmonic?
Yeah.
Okay. All right, hold on one second. So all right. And so then okay, so we know that
if CXP is harmonic,
Mhm.
then that inversion takes T to P and to T prime. So C and T prime P is cyclic.
Okay.
And we know that
I'm sorry.
I am getting confused.
Oh, because then since angle INT is 90, that means angle ICT is 90.
I am trying to prove that.
I lies on it. Well, we know that IC, oh, I guess we don't know that yet. So ultimately we're trying to show that ATB, sorry, B's covered up, but we're trying to show that A, B, T, and I are in harmonic conjugation. And then once we know that, if we can show angle ICT is 90 degrees, then that would prove that angle ACT is angle BCT. So that's what we're trying to do.
So we're going to prove I, T prime, A, B are harmonic.
Yes.
But isn't that a little obvious because
Well,
of the quadrilateral?
Well, actually, no. We know they're harmonic. We were trying to show that angle ICT is 90 degrees.
Oh, I see.
Yeah.
So the aim is to prove CT prime is the angle bisector of ACD,
Yeah.
right?
Yes. Yeah. That's what we're trying to show.
You also draw the intersection of Fi with xt prime.
Okay. It's probably this point, right?
Yeah, it's I'm trying to prove that with inversion that C lies on that circle Qi T prime N. And it seems
Okay.
obvious, but
So Dat, did you say you had an idea of how to do it just with the angle bisector theorem?
Maybe. So because X, E, and T is collinear, so we use Shiva for triangle X, A, B. So TA over 2B will be equal to KA over KX times LX over LB.
Okay.
And we need that will be equal to AC over BC, which is AL over BK.
We want AL over BK.
Yeah.
Okay.
Okay. So, and hold up.
It's all right. This problem's making me dizzy. There's just so much stuff. Okay, F, C, X, and P are harmonic. Okay.
I think it's obvious.
Oh, really?
It's a well-known thing.
That F, X, C, and P are harmonic?
Yeah, a triangle FAB, X is the orthocenter, and ACB is a point such that angle ACB is 90 degrees, and C is on FT.
You could probably bash it out. Okay, so once you know that, does that solve the problem?
It's from Brocard's theorem. I have proved it before.
Okay. Yeah, we're probably overkilling it, but yeah. All right, let's see if we can finish it up. So we want to show that F, X, C, and P are harmonic. Or let's say we know that. How does that solve it? Or does
Inversion with radius square root of FC times FP.
Okay.
Oh, F, X, C, and P are harmonic. Yeah, that is trivial because Fj and Fl are the tangent to the circle omega A, and Fp is a line passing through F and meets the circle FC in P. So by the harmonic, we have Fxc and P are harmonic.
Wait, are
It's
J and
FJ.
L, is Fj and Fl tangent to this circle?
Yeah, because angle ALF is equal to 90 degrees.
Ah, okay. So yeah, then it's trivial. Yeah. So we have F, X, C, and P are harmonic, basically because Fj and Fl are tangent to this circle. So Fj and Fl are tangent to omega A. So that means that Fxcp is harmonic. And then once we know that, invert about the circle with center F and radius Fn times Ft. T, and that's supposed to swap, so it swaps C and P.
Square root
It
of
swaps
Fn.
X and D because D is the midpoint of CP.
Sorry. So it swaps C and P, right?
Yeah.
So that means CNTP is cyclic.
TNTPI and the other point. TNTPI
IQ. Okay. And then that means angle ICT equals angle INT equals 90. So and then so since so now we're basically done because hey, where'd that go? All right, here. So since we have since AB, T and I are in harmonic conjugation, that means angle ACT equals angle BCT. So we have I think we got it, most of it there. So I think with inversion, there's a little bit I have to think about here.
Yeah, this may be fake solve or some more details may be needed.
Like, I think we don't really need to use inversion because like it just like power up the point, I think.
Power of a point, because basically it's like we don't know that the circle exists yet. Oh, I'm sorry, I hit the wrong one. But for this, like, yeah, is there a way to just use power of a point? So we have Fn times Ft is because if F is
Okay, I have another way. Yes, this is not true. We will do the same thing as in the triangle FAB.
oh, you know what? So Fn times Ft is Fx times Fd, and since those are harmonic, that's Fc times Fp. So yeah, we don't need inversion, right?
Yeah.
This doesn't show cyclicity because there can be 3 circles.
But I guess it shows that CNTP is cyclic, right? Because Fn times
This is not
Ft.
enough. Because CNTP, CQIP, and QITN can be 3 different circles.
Okay, because we have to show it pass through I. Yeah.
But there's another way.
There's another way?
The lemma I said in triangle FAB, if C is a point such that ACB equals 90 degrees and it's on FT, and
Okay.
X is the orthocenter, then FC XP is harmonic. If we apply this on triangle FIT, then we are done.
Interesting. All right, this seems really interesting, but I think I'm going to move on to the next problem just because we spent a while. But wow, there's a lot to this. So yeah, interesting. So here's our 4th problem. Oh, this one looks kind of hard. It's a simple statement, but yeah, let's see where we can go with it. So we have a triangle ABC, and we draw the Euler line. So let's see. So we have the orthocenter. So I'll say, and then H. So H is the orthocenter. And then S is basically any point. Yeah, this looks weird. So S is any point on OH, and it could be on the line. It doesn't have to be the segment, but I'm just going to draw the segment. And then we draw the 3 midpoints. You've seen problems like this in Vietnam before. So we call the midpoints MA, MB, and MC. And we have a new person joining us. So this is MA. Hi, Jonathas. Thanks for joining. So he's a new member from Brazil, and this is his first time. So welcome. So we're on our 4th problem. We have about 45 minutes left. So let's see where we can go with this. So we draw the 9-point circle. So that's basically the circle through MA, MB, and MC. And then we draw this segments through point S, and we see where they meet the circle. So MCS, MBS, and MAS. We let it intersect the circle at X, Y, and Z. And we want to show that AX AX, BY, and CZ concur. So this would be Z. Okay. So I'm going to hide a bunch of stuff. And let's see. Okay, so whoops. Let me close this. S lying on the Euler line, Pascal can come in handy. All right.
Maybe one homotopy would help.
Homotopy?
Yes, in the, wait, what is it called? The intersection of medians. The
Oh, the
centroid.
centroid.
Yes.
Yeah.
With negative 1/2 dilation.
All right. Let me make this a little.
That sends the circumcircle to the 9-point circle.
All right. Hold on just a second. That looks a little better, maybe. So AX. Oh, wait. Oh, I named these wrong. This should be. Oh no, I think I named everything right. Wait, is that right? Did I name everything right? Yeah, I think I did. It just looks weird. Okay, so yeah, that looks better. There we go. Okay, so let me draw the centroid. I forget, is the centroid like, well, that doesn't look right. Yeah, let me move S a little bit so it doesn't look like that.
What is the locus of intersection? Maybe we can use it.
So the locus of the intersection of AX, BY, and CZ. Let's see.
Can you label the altitudes from A, B, C, like the intersection of Euler circle with A, B, B, C, C, A?
Yeah, hold on just a second.
Yeah, yeah, I have an idea. Like this looks something like the Steinbart's theorem.
Whose theorem?
Steinbart's.
I don't know if I've heard of it. Interesting. Steinbart.
Right. So AX, BY, CZ is concurrent if and only if DX, EY, and FZ concur.
Okay, so EY, FZ, and DX.
Yeah.
Sorry, I turned in the chat. EY, FZ, and DX. Okay.
Like, can you connect them? Like, I just want to check if I'm right.
Yeah. EY, FZ. And it looks like they might actually concur on OH.
Yeah, that's why they give us like S line on OH, I think.
Interesting.
Like I think we can work out with Pascal and like the Steinbart thing that I'm gonna prove it later.
Okay. Okay, so we use Steinbart's theorem. And if we can show that those three concur, so EY, FZ, and DX, then that solves the problem.
Yeah, like the Steinbart theorem is just like you prove it with the Chevar's theorem, but with like the trigonometric version.
Okay.
Yeah, so they're gonna be calculations.
All right. Let me label the point that Sir Darwin. Okay, so this point right here, so I'll call it G, and then I'm going to unhide what I just hid. So we want to find the trace of G. So we want to see if we show the trace. So as we move S, whoops. It's not showing the trace very well. It's doing really badly at it. I don't know if it's a conic or something. Right, how do I make the trace go away? I think if
just undo it, yeah.
There we go. But yeah, I don't know. Is it a conic that G traces out? because it goes like way up there. I don't know if it's a circle or an ellipse or hyperbola. But yeah, I don't know. I'm not sure how hopeful that's going to be. All right. You guys want to try some of the last two problems, see if we can do those? I think one of them was easier. It's up to you guys.
Yeah, I'm nearly solved this one.
You solved
really
it?
Close to it. Yeah, I'm really close to it. Wait, just wait me 5 minutes.
Okay. Yeah, sure.
Like, cause I have met many like problem with like concurrencies like this, and like, the points are defined like have the same row like this. Yeah, I have met some of these before, and these problems in Vietnam are really hard. Like the Vietnamese mathematical Olympiad 7 problem last year. Yeah, it's very hard, and it's like similar to this.
Interesting. So the Vietnamese problem was similar to this one.
Yeah, like they like to, you know, like they define the points with the same row, like the same way, and then try to put like collinear or concurrent or coaxial.
Interesting. Cool. Okay, so we want to show dx, ye, and fz concur. I'm going to make these. I'm just going to draw up to the point G. Whoops. All right. Yeah, it's a cool diagram. And it's also interesting that these three concur on OH. I wonder if this point is like the isogonal conjugate of this point. I'd never heard of Steinbart's theorem before, but it seems interesting. So this is actually my first time hearing it too. I'm going to look it up on Wikipedia after the Zoom meeting.
Well, I don't think like it appears on Wikipedia because it's just like a lemma. Not really well known.
It's not popular enough. Okay.
Like, can you connect MAE and MBD? I think it lies on OH. And if that is right, then we are done.
MAE and MBD?
Yeah, it lies on OH. Yep.
Yep.
Okay, then I'm done. I'm gonna write the solution and the Steinbart theorem.
Okay.
So can I like send it like to our Discord? Like it's very useful.
Yeah, you can send it to Discord. Yeah. Or you could type it in the chat here. You know how to type, or yeah, you just send.
I'm gonna include a diagram so it looks easier.
Okay. Do you want to just do the whole solution of this on Discord?
No, just like the theorem, the Steinbart theorem.
Okay, just the Steinbart's theorem. All right. Let me take a look at Discord.
Let me write it out first.
Okay.
Is it sufficient to prove that that point lies on the Euler line?
I think Hans was saying that if we know that lies on the Euler line, then that would solve it.
Yeah, like M, A, and E are, the familiar points. So I think it's not really hard. Like they're just altitudes and midpoints, so we can prove it.
So do we know that, or is it something we want to prove?
Yeah, because I'm just solving it, and then it's sufficient to solve that.
Okay.
I think I know how to prove that.
How do you prove it?
I think in some last session we proved something similar, like when we take MAMB and it intersects ED, intersected.
ED. It's like these two, you mean, right?
Yeah, and take that intersection point and take that line with C.
The line that makes us C?
With C, yes.
Okay. Sorry.
Then that line is perpendicular to the Euler line that we proved like 1 or 2 sessions ago. But it is actually a radical axis theorem to prove that that is perpendicular. And then I think it is a Broca theorem to prove that actually that other intersection lies on the Euler line.
Interesting. Okay. Okay, so we could show that ED, EMA, and MBD. So I could write that. I'm just going to write up a little bit so far. So let ED and MBMA intersect at I. Then from a previous video, did you say IC is perpendicular to AC?
IC is perpendicular to the Euler line.
Okay, from a previous video. Whoops. And then so by Ricard's theorem, IC is the polar of S with respect to the circle. So IC, so S lies on so IC's, yeah.
So the Broca theorem would go like this. IC is perpendicular to the Euler line. So because the center of 9-point circle lies on the Euler line,
Okay,
then
so IC is the polar of S with respect to the 9-point circle.
yes.
And so, I mean, that basically solves it, because that means that that means that OS is perpendicular to IC. So
no, S is not the polar of IC is not the polar of S.
oh, sorry, IC is not the polar of S. It's MAE intersect Oh, you're right. It's the polar of this intersection point. So wait a sec. Yeah. So it's the polar of MAE intersect MBD.
I just sent in the theorem.
Okay. Hold on a sec. Okay. So I'll check Discord. Okay. So oh, whoops. It's a little. So if I is the in-center, and so D, E, and F are the points of tangency, and M, N, and P are points on the circle, so that DM, EP, and FN are concurrent. Then AM, BN, and CN. Okay, I like that. So once we know that, that solves it. Okay.
Yeah, and like the version 2 of it, like when the circle, the in-center becomes an arbitrary circle that meets each side at 2 points, then it was still right.
Okay, so instead of the end circle, it's an arbitrary circle, and
Yeah.
it meets the sides at DEF, MNP. So these don't have to be altitudes, right?
Yeah, like in the version that we're going to use, but in the original problem, that is the Euler circle. We're going to apply it to the Euler circle, and then we have like, we can prove it.
Okay, so
you guys want to work it out, or I'm going to send a solution?
Yeah, why don't you send the solution on Discord? Let's
I
see.
gotta write that down too. It's gonna take some time. Wait.
Okay. So yeah, I'm just gonna move on to the last two problems just because we're running out of time, but this seems like some really interesting stuff. Like it seems pretty cool. So I'm really glad that you brought it up. I appreciate it.
Yeah, it's a good theorem though.
Yeah, it looks really interesting. I've never seen it before, but it looks like really useful. So yeah.
Wait, why do I remember seeing it once on your channel before? Like
Steinbart's?
Yeah, I remember seeing it once, but I didn't learn it from your channel. I learned it from my teacher.
From your teacher. Ah, nice.
Yeah.
All right, I'm gonna move on to okay, so this one is from the European Girls Math Olympiad. So we have a triangle ABC, and we have some cyclic quadrilaterals. So ABDE. Okay, so D is a point on BC, and then we draw the circles ABDE and ACDE.
I saw this problem. It is actually easy.
Oh, it's pretty easy.
Yeah.
Okay, I'll just do it really quick and see see if we can do it. So maybe we did this one before, actually. I'm not sure. Line, so we draw the circumcircle of ABC, and AD meets it at P. And Q is a reflection of P across BC. Yeah, I feel like, I'm not 100% sure, but I think we did this problem before on my channel. So we want to show basically that AFQE is cyclic. All right, so we could try to show angle BFQ is AEQ. Let's see. So Q is a reflection of P. Just trying to think of the best way to know that. So BQCP is a kite, basically. And we just want to show that that's cyclic. Is BFQD cyclic? I don't know if we can use Pascal's theorem. Yeah, okay. So maybe it's just like Pascal's theorem. How do we show BFQD is cyclic? And then we use the same argument for CQED. So basically we want to show angle QBD is QFD, but QBD is E.
It can be obvious because angle BFD is equal to angle ECD from spiral similarity, and ECD is ACB, and that will be APB, and that will be APP will be DPB, and DPP will be DQB. So
yeah, I don't think you need a spiral similarity, do you? So like, or maybe it's the same. Maybe the angle chase is the same as a spiral similarity, right? So we have, but yeah, I think I got the same thing that you did. So angle QBD is angle CBP is angle CAP is CAP, which is CAD, which is angle CFD, which is QFD. Okay, so that means that BFQD is cyclic. All right. And then similarly, oops. Yeah, it doesn't like the spacing, I guess. So I'm just going to do this like this. See if that helps. And then similarly, CEQD is cyclic. And then we use Pascal's. So by Pascal's theorem, Q lies on the circumcircle of A. Yeah, that was easy. All right, we have one more. So I will, let's see, the last problem. I wonder, so sorry, I looked at this really quick, like for about 5 seconds, but I wonder if root BC inversion might help with this. So we have a triangle with a circumcircle. Then we draw the incircle. Touches it at D, and then we draw the angle bisector. I'm just gonna there we go. Okay, so let's draw a I, and it meets BC in the circle at E and F. Whoops. So it's Nah. I don't think it's going to let me do it unless I make it farther away. Okay, so that's E, and it meets the circle at F, and then we draw the circumcircle of DEF. And we have to draw the X circle. Okay, so I could try to use the in-center X-center lemma. So let me make this a smaller triangle. So just like that. So that would be the X center right there. Okay. And then, okay, so here's the X center. And the circumcircle of DEF, it intersects this X circle at S1 and S2. And we want to show that AT, what is T? Oh, it intersects this at T. Oh, we just want to show AT and J are collinear. So this is basically S1.
T is actually the touch point of the A mixed linear in circle.
Okay. I think I did a problem like that. We've done so many sessions that these are all coming together, but so T is the point of tangency of the mixed linear in circle. Okay. Okay. Oh, Jonathan, sorry I missed your comment earlier. Yeah, if we know QEC, I'm guessing you're talking about the previous problem. I'm just going to read, hold on a sec. If we know QEC and QFB, oh yeah, okay, yeah, you were going on the previous problem. Okay, so T is the touch point of the mixed linear in circle. So this looks kind of like a root BC inversion problem, right?
Yeah, that is actually really good to do root BC inversion because actually DEF circles should stay the same.
Really?
I think, yeah, because E would go to F and F would go to E. And actually, no.
Not necessarily.
No, actually, no, but it is fairly close, actually.
Okay.
So actually label the X circle touch point with BC.
Okay.
Then with the root BC inversion, J would go to T and vice versa.
Okay.
No, J does not go to D.
Or T?
T.
J go to D. Yeah, J go to D.
Yeah, because triangle ABT is similar to AJC, right? Is that true? I think so.
It is true.
All right. Oh, and then, okay, so really we want to show angle, we want to show S1 and J are isogonal. Actually, if you reflect S1 over AI, do you get J? I don't think so, but.
You would probably, yes.
Michael, what is S2?
Oh, S2, actually this point K really should be S2.
Okay.
The root BC inversion then would take DEF to EFJ.
Okay. So it takes DEF to EFJ. So wait, it swaps E and F, and it takes T to J. Is that the idea?
Yeah.
Okay. So okay, and then I mean, basically, we just have to show that. Okay, so we want to basically.
Hey, Michael, I'm like sending.
Okay.
I'm sending the solution of the previous problem to our Discord. Okay.
Okay, sounds good.
Yeah, I wrote it down.
All right, I'm just gonna paste it in. Actually, I think you can paste pictures on GeoGebra. Let me try it out. So let's see. I just want to see if I can paste pictures. I think there's a way to do it.
I'm not using GeoGebra though. I'm using another, another.
No, it's all right. But I think there's still like I think if you copy a picture from one file, even if it's not GeoGebra, I think there should be a way to paste it into GeoGebra. Image, here we go. Oh, but I have to save it. Oops. Let me download it. From webcam. Oh, I don't want to use my webcam. I want to use maybe I'll do it sometime later. But let's okay, so here's the lemma, and then here's the proof. Okay, so so the intersection of ME and ND are collinear. And since it lies on OH, since P lies on OH, then the other two, MX and NY, meet on OH. Okay, so Steinbart's theorem. All right, this looks pretty good. I'm not going to type it up in GeoGebra just because we don't have much time. But this will be part of the video that I upload to YouTube. It looks like a really good solution. So yeah, I'm gonna So basically we have mx, ny, and kz. They concur. Boy, where is z?
Yeah, I forgot to draw Z. Yeah, I was in a rush.
Oh, it's all right. So ax.
Like in a problem like this, you don't really need to draw Z because like they have the same role. You just need to like draw 1 or 2 points. So
Yeah, it's enough to
on
understand the proof. Just this. Yeah, it's enough. So since they all concur on OH, so what do we use about O and H in particular? Like, could it have been true with any isogonal?
Well, they give us the point on OH to prove that MX, like we need MX and Y and KZ to be concurrent. So they give us the point so that we can use the Pascal theorem to prove the concurrent.
So basically, this lemma right here, because like otherwise, without this lemma, it could really be like almost any 2 point. Like this lemma is why it's O and H, right? Because OH, EK, and FN concur on OH, right? So, okay, I think this makes sense. Yeah, this is really nice. This is a great solution. So yeah, thanks for bringing it up. I will just take one last look at this before we finish. So
we should prove that AS1 is equal to AJ.
Exactly. Yeah. Basically, we want to show S1 is a reflection of J over AG, right? So yeah, you said that this circle goes to circle EFJ, right?
Yes.
Okay. So basically, if we could show the circles are the same size, that would solve the problem, right? So basically, this circle, the X circle, or the N circle and X circle are swapped, right? Is that true?
In circle goes to X mixed linear circle.
Oh, the X mixed a linear circle? Under a root BC inversion?
Yeah. And the X circle goes to mixed linear in circle.
So these circles almost look tangent, but I don't think they are. Okay.
Wait, if the circumcircle of GEF meets OF meets circumcircle of ABC at T, then T is the mixed linear point.
Yeah.
Oh, I didn't know about this. How do you prove it?
Oh, I think it's because triangle ABT is similar to AJC.
No. We prove it because if you call T as the mixed linear point of the angle A, so you let FT cut AB, and you let the circumcircle with diameter AI cut the circumcircle of ABC.
Oh yeah. Okay. So
No, not that point. Not that point. Yeah, cut BC, not cut AB. Yeah, cut BC.
Oh, sorry.
Yeah. Yes, and the
Circle with diameter AI, right?
yeah. So that point in A and L will be collinear.
Okay.
Okay. So yeah, and NDF is collinear as well.
Yeah, so this is like a well-known configuration. It's like the Sharky Devil configuration. Yeah.
Yeah. Yeah. So if you use the inversion at F, so L will become T, N will become D, and A will become E. So A, L, N is collinear. Therefore, F, T, D, E is the cyclic.
Yeah,
Okay.
I get it. Thank you.
So that proves that P is the mixed linear point. And then I think there's like one more step to prove that AS1 is equal to AJ, right? I think we're really close. So I think you said the in circle goes to the X mixed linear in circle.
Yes.
Okay. That's weird. I always thought it just swapped in circle and X circle, but I guess I just don't know that much about it. Okay, so all right. I think I'll just leave the rest of it. I feel like I wonder if AJ passes through this point right here. Oh no, it doesn't look like it. All right, I'm just gonna leave this for the viewers since we're out of time. So we had a few new people on today. So thanks for joining. And we had a lot of really interesting proofs from everyone, both the new people and the people that have been on it before. So I appreciate all you guys sticking around for the 3 hours. If anyone watching on YouTube, if you want to join, feel free to email me at mgreenb801@gmail.com. The sessions are at 8 a.m. US Central Time. So thanks for watching and have a good day.